So we're going to work through some kinematics. I want to reinstate this chart. I think it's really helpful and very important. So for each of these, I want to just check off which variable is relevant for that particular equation, because we've got these four equations, and the order is not important. They're all on your equation sheet as well. You've got delta D, VO, VF, and T in this one. In this case, you've got V initial, V final, A, and T. In this one, you've got delta D, VO, T, and A. And in this last one, we've got V initial and V final, A, and delta D. So for all of these, you'll notice there's one thing that's not present. There's one variable. So this one doesn't have acceleration. This one doesn't have delta D. This one doesn't have V final, and this one doesn't have T. So that actually is super useful for figuring out what equation to use when, because you're going to need to be able to choose which one of these. So you're always going to make a list of all givens and what you're solving for. And we've been learning how to do that all along. So I always make a little list. I go V initial, V final, A, delta D, delta T. It's a different order than that. It's just the order I've memorized. And I always make myself like a little chart, and I write down everything I've got. And then I look for, generally, which thing I'm missing. And the thing that I'm missing tells me which equation to use. So like this one, no acceleration can't be in your given or what you're looking for. This one has no delta D, this one has no V final, and this one has no time. Notice that V initial must be in all of them. So there's no equation that we have that doesn't have initial velocity. So that's a variable that you always want to make sure you have, or that's what you're looking for, okay? What does it mean to undergo constant acceleration? Because these four relationships are only true for an object that's undergoing linear motion with a constant acceleration. Constant acceleration is not the same as constant velocity. Constant velocity means acceleration is zero. Constant acceleration just means that if your velocity is changing, it's changing at the same rate every second. So in other words, I might say I've got a constant acceleration of 1 meter per second squared. Well, that means my velocity is changing at a rate of 1 meter per second every second for the entire time. So this is an important distinction. You'll see this a lot, and I just noticed that there's a lot of students who then confuse the two, and when they see constant acceleration, they assume that acceleration is zero, but that's only when it's constant speed. How can you tell the difference between speed and acceleration in a problem? So the easiest way is looking at the units. Speed is in meters per second, acceleration is in meters per second squared. This is the easiest way to distinguish between the two. What is the difference between average velocity and final velocity? Average velocity is your delta D over delta T. And this is taking your total distance divided by your total time. So in other words, if you have an object that's moving from here to here, here's your V initial, here's your final, your average is going to be over the whole thing. You're either going to use this equation, or you can do 1/2 V initial plus V final. That's going to give you your average velocity. Whatever it is here, plus whatever it is here, because you have two numbers, you divide it by 2. Final velocity is an instantaneous velocity. Instantaneous velocity, whatever it is at the end of the segment that you're examining. So I put this in here. I didn't used to have this in here, but this is kind of important because this is something that so many students make mistakes on. And I don't say that to make you feel bad. I just want to address it because it's really a source of confusion. These two equations are perfectly legitimate equations. They are physics equations. They are the definitions of average velocity and average acceleration that we have been using for the entire 5 weeks that we've been working on this unit so far. You are allowed to use these when appropriate. Also, just like we just discussed up here, right, you can also use this if you're trying to find average velocity, but we rarely do that one. So when are you allowed to use this equation right here, this average velocity? Only when asked specifically for average velocity. That's it. Or if you know that it's constant speed. So those are the only times when you're specifically asked for average velocity or you know for a fact that it's constant speed. There are no other incidences where you would use that equation. And I have to mention it because there's so many people who automatically try to use this equation for any problem that I give them, even when it's not appropriate. These 4 equations are when you have acceleration. This equation is when either you're assuming no acceleration or there actually is no acceleration. Excuse me. So you might see a problem like this. There's a cart rolling along a horizontal surface and you measure the cart moves a distance of blah, 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 over a time period of blah, blah, blah. What is the average speed of the cart? Well, they're asking you specifically for average speed. Then you're allowed to use it. Okay, the last thing I want to add in here before we start some problems is I want you to recall these things about free fall. So free fall applies whether you're moving up or down. So you can throw a ball straight up, or it can be dropped and it can move straight down, or it could do both. It could go all the way up and all the way back down. As long as gravity is the only force acting on an object, right, where you have no air resistance, then you are allowed to assume it's in free fall. For free fall only, this acceleration is a given. It's so nice when you know it's a free fall problem because then it means you automatically know acceleration. One issue that I find with student work is that they assume acceleration is always 9.8 even when you're not in free fall. That would be incorrect and means you do not understand when it's appropriate to use this value. The signs are especially important for free fall. I mean, it's important for all problems, but especially important for free fall. Don't forget to make downward displacement and downward velocities negative. You can still use any of these equations. So whether you're moving on the horizontal or whether you're moving vertically, like in free fall, you're still only using those 4 equations. So let's start some problem solving. We're going to do these 5 problems. This might be a longer video. You can see just going over the basics already took us about 8 minutes, so bear with me here. A car accelerates from 15 to 30 meters per second in 4 seconds. So let me just align this a little better. So we've got a picture first, always sketch it out. We've got V, X, T for both of these positions. We always draw initial, final, and then we label. You can label it 0 and 1 or 1 and 2 or A and B or initial and final. I mean, I don't care what you call these as long as you show them. What do we know? We've got the initial velocity. We've got the final velocity. The initial position and initial time are almost always 0 unless you're told otherwise. It took 4 seconds to do that. We don't know how far, but that's what we're looking for. Right? That's my unknown. Sometimes I'll circle it or I'll just put a question mark. Acceleration is in between 2 velocities. We don't know it. We're not asked to find it, so I'm not going to do anything. I also make that little chart that I mentioned before. Even though I have it here, I've just always found this so helpful just to make sure that I'm interpreting the problem correctly. It is not a requirement, but a very strong suggestion. You know, people pay me a lot of money to tutor them, and this is what I show them to do, and when they use it, they do well. The last thing you need before you start solving is you want to show the direction of velocity, and you know you're increasing speed, so acceleration is that way too, so you know they're both going to be all these are going to be positives. So what equation has everything except for acceleration? Oh, it's this very first equation. So we're going to rewrite the equation. So this is 1530 times 4. So that's me 45 times 2, which is 90 meters. A kid goes down a slide, starting here, ending there. Again, VXT, VXT. I'm just going to make my x-axis go down that way. We're going to assume it starts at rest. Position initial is 0, right? So we're just going to label this. Notice it doesn't take a long time. If I'm going too fast, then you certainly should pause the video. I'm filling in what I know. They tell me it takes 3 seconds. This is the acceleration. I know it's acceleration because of the units. Acceleration is between 2. There are 2 issues that I often see here, is that people throw this in for final velocity, or they don't show acceleration between. They show it at one location or another. You might think these are trivial matters, but they really make a difference in terms of your results and how consistent you can answer these questions correctly. So again, I'm just going to rewrite this. It doesn't take very long, and I find it worthwhile. So I go over here, I look for which value. We don't have the final, so I'm going to pick that equation. These equations are on your equation sheet. You do not have to memorize them. You'll have to forgive me because I've been doing this for a very long time, so I have memorized the equations. So if I go quickly and I don't have to refer to that, that is why. And you will actually find that eventually you learn them too. So notice this is going to be 0. 0 times 0 times 3 is going to be 0. So I kind of did that in my head. I'm going to also write it out because I want you to see where I'm getting these values from. Oops, this should be 3. I also want to talk about units a little bit. Let's just do the math first. 1/2 times 1 is 1/2 times 9. Half times 9 is 4.5. So notice, always put units on my work when I'm doing the labeling. You make sure you put units on everything when you're just labeling stuff and on your answer. You do not need units in this step, right? In this middle step. You'll notice what I do. I'm very consistent here. I put units everywhere where I'm labeling stuff. In the math steps, I don't put the units. I find it really confusing to do that, so I don't. So an automobile set the world record for acceleration, increased speed from rest. So let's see, we have a car. VXT, VXT, in between is acceleration. You can kind of do that setup even before you finish reading. I'm going to make positive this way. Increased from rest to 27 meters per second. I have the time, 3.07 seconds, and I want to find how far it traveled. I don't know the acceleration. So notice I'm missing my displacement this time. So what equation doesn't have displacement? That's this second one. So again, you can make your little chart to figure that out. If you know, it's easier sometimes in a vertical list than it is, and it only takes a second to do. So you're going to do V final equals V initial plus AT. 27 equals 0 plus, oops, that is not the right one because we want the one, we're solving for displacement. We don't have acceleration. I picked the wrong one. We're back at the first equation. So let's cross that out and do that again. So hopefully you were wondering what I was doing and you caught that mistake. This math I cannot do in my head. Let me take out my calculator. And it's going to be 0.5 times 27 times 3.07, which is 41.4 meters. Done. A rock is tossed up with an initial velocity of 2 meters per second. How far does it travel before reaching max height? So V, Y, and T, it's on the Y-axis now. Oh, and I forgot my motion diagram here, by the way. So I'm going to add that in. V, Y, T. Now, when you're doing a free fall problem, which this is, sometimes it seems like you don't have enough information. Like it says if you have the initial velocity of 2, and you're trying to find how far it travels, that's this, it looks like you don't have enough information. So what are you missing? that they don't say? Well, there's some important things about free fall that you've got to know because it's characteristics of free fall. First of all, this initial position and time, the bottom is going to be 0 and you're starting your stopwatch here. We don't know time, but we do know that the velocity at max height is 0. Yeah, it's in the notes, but it's not on this paper. When you get to maximum height, right, at max height, this is part of the definition, V final is 0. So on the y-axis. So you can put that in as a given, and you know acceleration is negative 9.8. So when you make your V initial, V final, ADT chart, you're going to have 2 meters per second, 0, negative 9.8, and you want to find displacement. So you don't have time. So you need an equation that doesn't have time in it, and that one, no time. So we're going to use this equation. So V final squared equals V initial squared plus 2A delta D. So this is 0 squared plus 2 squared equals 2 times negative 9.8 delta D. So this is negative 4. This is negative 19.6. So this is going to be positive 0.2 meters. So you're not going up very high. It's just going up a teeny little bit. Okay. Last one. In 1991, 4 English teenagers built an electric car that could attain a speed of 30 meters per second. Suppose it takes 8 seconds for this car to accelerate from 18 to 30 meters per second. What's the average speed? And then part B is asking for the acceleration. So here's the first problem where we're really dealing with an average speed question. So I'm going to not do anything different from the previous ones. So we're going from 18 meters per second to 30. So that's increasing speed. This is my positive direction. And we want to know what acceleration is. And we got this time is 8 seconds. We don't care about that. So this is for part B. Part A is asking for average velocity. Well, average velocity, in this case, you can do change in distance over change in time, but we don't know distance. So, you know, that makes me think about, oh, let me do it this other way that I mentioned to you before. So it's just 18 plus 30 divided by 2. So you've got 48 divided by 2 is 24 meters per second. To find the acceleration for part B, we've got 18, 30, this we want to find, this we don't know, this is 8 seconds. So we want an equation without delta D, so that'll be V final equals V initial plus AT, and this will be 30 equals 18 plus A times 8. This will be 12 when you subtract that over. So 12 divided by 8 will be 1.5 meters per second squared equals acceleration.